Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. In the real world, good enough usually isn't enough. Engineers want the maximum strength for the minimum weight, and businesses want the maximum profit for the minimum cost. Calculus gives us the tools to find these optimal points mathematically, and we call them extrema. Now, before we dive in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. So now we're going to jump in with some definitions. I'm sure you already know what a maximum is and what a minimum is. But now we're going to introduce the idea of absolute maximum and minimums and local maximum and minimums. We say a function f has an absolute maximum at c if f of c is greater than or equal to f of x for all x within the domain of f. And similarly, for absolute minimum, f of c must be less than or equal to f of x for all x within the domain. So just like what the term suggests, absolute max and absolute min are the absolute highest and absolute lowest point on the graph. Now, a function f has a local maximum at c if f of c is greater than or equal to f of x for all x in an open interval containing c. So the important part here is that it has to be an open interval. And again, similarly, f has a local minimum at c if f of c is less than or equal to f of x for all x in an open interval containing c. So let's take a look at this graph here to see what we're talking about. So to find the absolute maximum, all we have to do is look at the entire domain and find our highest point. So in this case, here would be our absolute max. And then the absolute minimum will be the lowest point on the graph, which would be this point right over here. So this would be our absolute min. Next, we're going to label our local max and our local min. And you can think of local maximum as the top of a hill and the local minimum as the bottom of a valley. So if we're looking at this graph, we can see that right over here, we have a local max. So this here is a local max. And then as for local min, we have one right over here. So this is our local min. And then we have another one, which is over here. So this is another local min. So notice that a point can be both an absolute minimum and a local minimum. Similarly for being absolute max. A point can both be the absolute maximum as well as a local maximum. However, the important thing that you need to know is that your endpoints on a graph can never be a local extremum. And the reason is because we cannot create an open interval containing the endpoint. So therefore, the local extrema are only going to exist in the middle of the graph. Next, we're going to take a look at a theorem called the Extreme Value Theorem. The Extreme Value Theorem says that if f is continuous on the closed interval AB, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, as some numbers, c and d, that are within the closed interval AB. So a couple of important points. First one is that f has to be continuous. And next, it is on a closed interval AB. So let's take a look at why that's important. So we're going to draw a couple of examples here to demonstrate this. The first example, we're going to draw a graph that follows all of the constraints. So meaning f is continuous and it's continuous on a closed interval AB. So let's say our graph looks something like this. So this is our A, and then the graph looks like this, which means over here, this is our b. Now this function f is continuous on the closed interval AB. So therefore, it must have an absolute max and an absolute min. And we can see that that is the case. We have our absolute max right over here. And then we have our absolute min right down here. Next, we're going to take a look at what happens if f is not continuous. So let's say our graph f looks something like this. We have a point here, and then it looks like this, So here we have our A is here and our B is here. So again, here our interval is closed because f of A and f of B are both defined. However, this function is not continuous. So what happens here? Well, we can see that as we get closer and closer to A, the function is getting smaller. However, if we actually get to A, f of A suddenly jumps up. So there isn't a particular x value that will give us a minimum. So which means we don't have an absolute minimum here. And same thing for the maximum. We can see that if we follow the graph, when we get closer and closer to this value, it looks like we're about to hit a maximum. However, when we actually get there, the value jumps down. So again, we don't have an absolute maximum. So therefore, here we have no absolute max or min. And the reason is because our function f is not continuous, which is why f must be continuous in order for us to use the extreme value theorem. And next, we're going to take a look at one more example where f is not on a closed interval. So here, let's say f looks similar to the first one we drew, but it is an open interval AB. And now you can see that we still have our absolute minimum because it happens to be somewhere in the middle, but we don't have an absolute max here. So this is the absolute min, but no absolute max. And this is for the same reasoning as the second example, because that absolute maximum point has now been removed. So we can get closer and closer to it, but we can never actually get there. And this is why we must have f being continuous on a closed interval. And now let's do a quick recap of what we covered in this video. We learned that extrema are the high and low points of a function. And when we say absolute, we mean the absolute top or the bottom of the whole domain. Local is just the top and bottom of a small valley or a hill. And lastly, we went over the extreme value theorem, which has two requirements. The first one being that it has to be a continuous function, and the second one being that it is continuous on a closed interval, denoted as brackets, not parentheses. These definitions and understandings allow us to start exploring the connections between calculus and real-life extrema, which we will dive into in the next video. And now it is your turn to give this a try. Can you answer the question on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.